Hi. Okay, so really this section, as far as vocabulary, is really kind of simple. You have three major terms. You have one that is what is probability, right? So probability is one of them. The second part of this is about what is called the law of large numbers. And the third part of this section is going to be about what are simulations. Okay, so you have probability, the law of large numbers, and simulations. All right, so let's look at first probability. So let me back this up, get rid of everything but probability. Backing up. Okay, so probability is basically you have a chance process. Okay, so you have a process that somehow can be repeated that involves chance. Okay, and the baseline understanding of probability, sometimes we call this the experimental probability, is the idea that I repeat this chance process over and over again, and I look at the proportion of times that this chance process gets a certain outcome. Okay, so I identify an outcome that can be a result of this chance process. I repeat this process over and over and over and over again and say what proportion of the time does this outcome occur. So probability is a metric on a scale from 0, meaning it won't happen at all, to 1. It always happens, okay? And most events, most outcomes of a chance process happen somewhere between 0 and 1. Sometimes it happens at 0, like, if you roll a 6-sided die, the probability of a chicken popping up is 0. Or if you roll a 6-sided die, the probability of getting a number from 1 to 6 is 1. Okay, and most outcomes of a probabilistic event, a chance process, land between 0 and 1. And this is the idea of experimental probability. It's like if I did this chance process over and over again, what proportion of the time, right? So like here, if I was at like 0.40, right, that means that 40% of the time I would get this outcome when this process repeats, okay? Now, there is another idea here which is called classical probability. Which is a little bit like not exactly the definition, right? So this is like the classical or theoretical model, right? Which means like if I can examine the event and look at the number of possible outcomes, right? And then I look at the number of outcomes where my outcome happens. This will give me a classical probability. So, for example, like the number of possible outcomes on a 6-sided die is 6. The number of even numbers is 3. So that would be 1/2 or 50%. Now, normally when we're talking about probability, we're talking about the experimental probability. Okay? This is a theoretical model of the experimental probability by examining the chance process itself, right? But it's a theoretical model. Now, if the theoretical model is good, then it should follow what we're about to call the law of large numbers. Okay, so the law of large numbers, law of, there we need a word of, large numbers is actually a way of relating the experimental probability and the classical or theoretical probability. Basically, what the law of large numbers says is that as your number of repetitions of our chance process increases, the experimental probability, right, is going to approach the actual probability. So, like, this is literally the probability. The actual probability is the probability you would get if you did like an infinite number of trials, which is what we hope that the classical probability is, right? So, like, doing 1 repetition is not going to get me there. Doing 10 repetitions is not going to get me there. But if I do like 1,000 repetitions, what I should see happening in a non-chaotic system is that the probability, the experimental probability, the probability that I'm getting by doing a lot of trials should start approaching some number, right? So that proportion should lock in on some number, which is what we call the actual probability. Now, if I have a good model, that good model should be giving me the actual probability. So what we want is that if I have a good model, right, then the law of large numbers says that the limit as the number of repetitions of my chance process, right, the number of trials approaches infinity of the experimental probability should approach the classical probability. Okay, so if I have a good model and my classical probability model or my theoretical probability is accurate, then this should approach that. Okay. Now, it doesn't mean like it's going to like every time that I do another trial, it's going to get closer. It does mean on the whole, there's going to come a point where I stop getting further away, right? So there's a little bit of a wiggle room there. And if you've done anything with like calculus and limits, that kind of makes sense. But so if you kind of like look at this, and here is my number of trials, right? My n, right? And this is my true or my actual probability, right? Then as the number of trials increases, the experimental probability is going to like get closer and closer and closer to that actual probability. And if I have a good model, then my classical or theoretical probability will be equal to that true probability. Okay, so this is what we're talking about with the law of large numbers, right? So, the question is just like how many numbers is large, right? Well, that depends on how precise I want my probability, how precise I want to be. Whoops, I moved you. There we go. I'll move you back. There you go. How precise I want to be to the actual probability, right? So if I keep doing more and more and more trials, I'm going to gain in precision. I'm always accurate, right? I'm always centered around the actual probability by repeating this chance process. But more and more and more trials should move me to a greater sense of precision. Okay, so then we're going to get into simulation. All right, so what is simulation? Okay, simulation is where you have 2 chance processes. Okay, 2 different chance processes. And what you do is like, okay, so over here I have my chance process. So like, let's say the biological sex of a baby, right? biological sex of a baby is a chance process, right? Generally speaking, the probability of getting boy is 0.5, probability of getting girl is 0.5. So this is, there's a certain point here where, because of the Punnett squares, right, x, y, x, x, right, we have a sense here where the model of best fit gives us 50-50 chance for each conception of a child for the gender to be one or the other, right? So that's one chance process. A similar chance process is a coin toss. Okay, so probability of heads on a fair coin versus probability of tails on a fair coin is 0.5 and 0.5, right? So what we notice about these two chance processes is that the probabilities for the possible outcomes are identical. Okay, which means that we can use one of these processes to simulate the other. Okay, and let's say I wanted to simulate like 1,000 childbirths. Okay, so what I could do is, instead of actually producing 1,000 new babies, I could just toss a coin 1,000 times and say this could stand in for this because the probabilities are the same in these two models. Now, in theory, I could, simulate the coin toss at the beginning of like a football game by producing a pregnancy, right? So that could happen. It's not really a good idea. I mean, we're gonna make a baby every time we're gonna figure out who gets the ball first in a football game, but one could simulate the other, right? Now, why is it a good idea going in one direction and not in the other? Usually, when you're doing a simulation or some sort of model, you want the chance process that you're using as the simulator, right, in the simulation to somehow have a lower cost than the one that you're simulating, right? So it makes sense to use a coin toss to simulate the result of a pregnancy. It does not make sense to use a pregnancy to result the simulation, or to simulate a coin toss, because the coin toss is a much more low cost reality. And usually we measure cost in either terms of money or time or effort in some way, shape, or form, right? So what we're usually looking for in simulation is a way to create the same probability distribution, which is something we're going to get into in the next couple of classes here, without actually incurring the same cost, right? So we want to lower the cost to create the same set of outcomes by using two chance processes that have the same model. Okay, so there's your three things for this section. You have what is probability, right? So the probability is, as we keep doing a chance process over and over and over again, how often, how frequently, or what percentage of the outcomes are getting a particular outcome, right? Law of large numbers says that number should actually exist, right? So that as you continue to do a probabilistic process, you should actually land on a limit. So if you think about this, not everything is guaranteed that a limit exists, but in a probabilistic situation, a chance process limits should exist like this. So as I do more and more and more and more trials, I should get closer and closer and closer to a particular number, which is what we're going to call the actual probability. And then simulation are when you exchange one chance process for another, where the two processes have identical probability distributions. And usually you do this in order to gain, because the one process has a lower cost in some way, either time, money, effort, risk, whatever, to the other one. So this is what we do. All right, so there you go. Probability, law of large numbers, simulation.